welcome to The Explainer. Today, we're going to break down something that's super fundamental in stats, the difference between discrete and continuous probability distributions. Now, I know that sounds like a mouthful, but trust me, it all boils down to one really simple question.
So just think about this for a second. What's the real difference between things you can count and things you can measure? Like counting the number of people in a room versus measuring their exact height. That one little question, it gets right to the absolute heart of what we're going to cover.
Right, so on one side, you've got stuff with distinct, separate values. You can have 27 students in a class, but you can't have 27 and a half students, right? Or you roll a die, you get a 4, not a 4.2. But on the other side, we're talking about things that can take on any value within a range. Your height isn't just 175 or 176 centimeters. It could be 175.321, and you could keep adding decimal points forever. This very distinction, counting versus measuring, is exactly what separates our two big topics for today. All right, so let's dive in and actually give these ideas their proper names. It's time to formally meet our two different types of distributions. First up, we have the discrete distribution. Honestly, just think of this as the expert in handling anything you can count, one by one. You know, like the number of heads you get when you flip a coin 3 times. You can get 0, 1, 2, or 3 heads, but you can never, ever get 1.5 heads. They're just distinct, countable results. And on the flip side, we have its counterpart, the continuous distribution. This one is the specialist for data that you measure. It can take on any value at all within a specific interval. A great example is the time it takes to run a race. It could be 10.1 seconds, or 10.11 seconds, or 10.112 seconds. I mean, you could just keep going. There's literally an infinite number of possibilities inside any range you pick. Okay, so now that we've met them, let's put them head-to-head to really see how they're different in practice. So yeah, the most crucial point is just the type of values each one deals with. Discrete is all about countable, distinct numbers. Think integers, right? 0, 1, 2, 3. Continuous, on the other hand, can be any value you can think of inside a range, an infinite spectrum of possibilities. Okay, so how do we actually calculate probabilities with these things? Well, for discrete data, we use something called a probability mass function. Let's just call it a PMF. And it's a really straightforward idea. The PMF gives you the probability of one specific outcome happening. So, what's the probability of rolling a 3 on a regular 6-sided die? The PMF tells you, plain and simple, it's 1/6. Now, for continuous data, things get a little weirder, a bit more abstract. Here we use a probability density function, or PDF. The reason is, since there are infinite possible outcomes, the probability of landing on one exact single value is basically 0. So instead, the PDF helps us figure out the probability that a value will fall within a certain range. And this right here, this is a really important, kind of mind-bending fact. Just think about it for a second. What is the probability that someone is exactly 180 centimeters tall? I mean, exactly 180.00000 with infinite zeros. Well, because there are infinite other possibilities, the chance of hitting that one single precise number is 0. It's just impossible. And that's why with continuous data, we always have to talk about ranges. Okay, so visually, this is what a discrete distribution looks like. It's a bar graph, and it's super simple. The height of each individual bar tells you the exact probability for that specific outcome. Easy enough, right? And now for the continuous graph. See how different this looks? It's a smooth curve. And here, we don't care about the height at any single point. What matters is the area under the curve between 2 points. So if you want to find the probability of a value falling in a certain range, you calculate the area in that slice. A wider range means more area, which means a higher probability. Makes sense. But for all their differences, they have one absolutely crucial thing in common. Whether you're adding up the heights of all those separate bars, or you're calculating the total area under the entire curve, the total probability for all possible outcomes has to equal 1. I mean, something's got to happen, right? So the total chance is always 100%. Okay, that's the theory. But where do we actually run into these things out in the wild? Well, let's take a look at some of the most common families of distributions that you're likely to encounter. So for discrete data, you'll hear names like the binomial distribution. That's perfect for things with 2 outcomes, like a coin flip being heads or tails. Or the Poisson distribution, which is great for counting how many times an event happens over a period of time.
Then for continuous data, the rock start is definitely the normal distribution. You know it, it's that classic bell curve you see everywhere. It's used to model tons of stuff like IQ scores or people's heights. But before we get into the nitty-gritty formulas, what are we even trying to calculate? Well, usually two main things. First, there's the mean. That's really just the expected average value. It's what you'd expect to get on average if you ran the experiment over and over and over again. And the second thing is the variance. All this tells you is how spread out the data is from that average. Is everything clustered tightly together, or is it all over the map? A small variance means things are really consistent. A big variance means, well, your results are all over the place.
So how do we find these for discrete data? The math is actually pretty intuitive. We use summation. You'll see it as that big Greek E-looking symbol, sigma. All it means is add them up. You just take each possible outcome, multiply it by its probability, and add all those little pieces together. But for continuous data, you can't just add up a list, right? Because there's an infinite number of values. So we have to bring out the big guns, calculus. We use something called integration. That's the long curvy S symbol. And you can just think of it as a super-powered way of adding up an infinite number of incredibly tiny slices from under that curve to get our answer.
All right, let's wrap this all up. If you're going to take anything away from this, here are the crucial points to remember.
Honestly, if you can just lock in these three key differences, you'll have a solid grasp on this whole concept. Number one, it all comes down to countable versus measurable. That's the big one. Number two, are we calculating the probability for an exact point or for a range of values? And number three, just picture it in your head. Is it a graph with distinct bars or one with a smooth, flowing curve?
So I'm going to leave you with a final thought to chew on. This isn't just some abstract theory from a textbook. Just look around you, right now, wherever you are. What can you count and what can you measure? The number of lights in the ceiling? That's discrete. The exact amount of time left on your lunch break? That's continuous. The number of unread emails in your inbox? Discrete. The precise weight of your laptop? Continuous. See? Probability isn't just math on a page. It's literally a language for describing the world all around us.